know he uses OneNote with, I guess, he pre-defines problems in there, and then he works with them. So he does a good job, but.
I agree, and I don't think
What's
news, I would agree that they're mind numbing, but I don't think News Solution fixes that.
No.
That's a mind numbing class right there.
I didn't know. I really, frankly, what I'm trying to do is come up with a compromise where if I do go through something, to use something, I want to be able to write problems down and work on, and everybody like work with me. I mean, in a way, it's better for the permanent record, but still to this day, the best classes that I've ever had and that I've ever seen have always been taught on the board with the slides and stuff like that we used to complement. They may have a slide that shows, you know, our radar array, then they go through the solution.
The .cam is a good compromise.
Well, I think like the benefit of the DocCam too is like if you're writing on an 11 by 8.5 sheet, it's easier to take notes because if you're on the board, like a lot of professors, you do this sometimes,
Well,
where you just kind of go back and forth and it's like really hard to organize it on a sheet.
what I try to do, the formulas I'm going to be going for and getting over and over again, I'll put on one porch on the board, and then I'll keep on referring to them. Now, I do that a lot with signals and systems. This class, because we're spreading out over information theory, signals and systems, and EMAG, it's something where I've got to dabble with a lot of different things, so I can't just put a list of formulas down. But I did want to talk about some stuff that the chapter 4 throws a lot of things in there that are they're just skimmed at the surface level, and you have to almost accept it as truth. For instance, the correlation distance, capital P, if you've done your reading, you know, he talks about that. That's the distance over which there's an actual relationship between surface points. Right? Then there's a thing called the mean squared, what do you call it, surface error. And that's really the RMS surface error, which takes the actual height, there's a mean value, and it goes in and squares the difference in the actual height and the mean height, and it goes through as an integration, and then it takes the square root of it. All right, it's just like RMS voltage, only it's for 2 dimensions. Well, he doesn't show you where it's used, and then he comes up with a lot of other things that he just skims. I'm going to tell you this stuff, and then we're going to talk, well, first, do you have any questions about the homework? They were straightforward problems. They were, if anything, almost too easy. I should probably do one in fairness to you. I'm not going to give you an oblique incidence wave problem where you have to figure out any kind of Fresnel reflection coefficients or anything like that. By the way, I didn't say this last time because I assumed it. When we use the Fresnel reflection coefficients, we have either gamma, say it's TE, a TE wave, and there's this is some function of incident angle, right? And I don't want to write the equation over and over. Just follow me and see it. Now, when we have that, well, what does that really mean in terms of a problem? Well, here's what Fresnel really does for us. If you use his, you're using this angle. I think he calls it the gamma right there. And you're using this angle. This is the incident angle. Angle of reflection is this. You don't worry about the transmitted angle because this is going to be something that's a soil or something like that. And the Fresnel reflection coefficient at this point, if it was for TE, for instance, you don't need to write this down. We know we always have N2 minus N1. I like to use intrinsic impedance as not index of refraction. That's the way I've always done it. Then it's over N2 plus N1, and then there's going to be the cosine of theta incident, cosine of theta transmitted, and then cosine theta incident, cosine theta transmitted. This becomes a sine of theta, from sine of gamma, and this is gamma transmitted, and this is the sine. Let me just do this one time. But I'll tell you where I'm going with this, just so you understand. You can go ahead and use Snell's law to get rid of this term here. But when you get that, what it really means is if you have an E field incident here, E naught incident here, it's in the TE mode, then this scattered field will be E naught incident right there, times the reflection coefficient for the TE mode. That's what it means. Now that's the electric field, it is not the power. Right? The power reflected, if you wanted power density, then you're gonna have to say, if you wanted P reflected, that's 1/2 the magnitude of E reflected squared over eta in region 1. Now you have to take this term and square it, and you see power reflected is proportional squared of the reflection coefficient. And that's very important to understand. It's always proportional to the square. So if this thing is 0.5, the power reflected is 1/4 of the actual incident power. Follow me on that? And that's something you have to keep in mind. And there's a few other things, but I didn't actually see that. And when he goes through the diffraction coefficient, and he has, he's gonna have an F squared term, that is multiplying the power that's incident. And the power incident times that F squared is how much power density is actually refracted in the different regions. And he goes through that. Well, he talks about, he doesn't do a problem, which I'm not really fond of. So now, with this chapter, here's the things you need to be aware of, and I'll tell you if you use an equation or not. This is the end of chapter 4. I'm not worried about a lot of the stuff that he has where he refers to RMS surface area and a correlation distance, because that's later on. That comes later in the course where we do a number on that. But there are some things you have to understand, and I mentioned this before. It's the divergence factor. And I want to tell you one thing about this. You don't have to worry about the equations. You have to be aware of the problem. You can look at the equations if you need them. And this is for very large scale systems. So it's something that's an airborne, something like an AWAC or an orbiting satellite, you need to be aware of this. But this is the radius of the Earth, A. And you have something at a height HT above it. This would be of the order of 50,000 kilometers or higher, something significant, not something small. Then what happens is, as the signal hits here, I'm going to just try.
You say 50,000 kilometers or meters?
Meters. 50 kilometers. Right?
Gotcha.
Would that be very high Earth orbit? Probably, I don't even know if you could orbit that high. Yeah, I suppose you could. It would be a long way. Anyway, for this, if you have an antenna and the beam width is small here, so this is going to be some beam width there. But when it scatters, what actually happens is the beam broadens. All right, if you just do a ray trace, bang, bang, that way, right? Ray tracer, smaller, you get a much broader angle. And as you get to the actual top here, then you get a real bloom. You'll see a whole lot of things that happen here. We get diffraction, then you get all sorts of surface waves and things like that. Now, you need to be aware of that only for large radars that are, I'd say, very high altitude. Satellite, low Earth orbit satellite, for AWACS, and I can't think of all of them. But normally, for most radars that are either terrestrial based or low altitude, you never worry about that effect. And it really has to do with how much of the power density is lost out here. You don't need to do it. So I don't talk about it. Now, this I do talk about, and this is the biggest problem with Doppler radars, clutter. And I've mentioned before when my dog, the sheriff's deputy took the thing and just, and he took the spot and he moved it down, the actual point the radar gun was aimed at, and just with his wrist did this, and it was 69 miles an hour, 68 miles an hour. I forgot. There's nothing moving except his wrist, and where the point was that it's hit. So it's apparent motion. Well, planes, anything that is moving, including a police vehicle moving in a direction, the actual velocity he measures of the car is the rate of closure to himself. That's it. All right, so he needs to exactly check. I mean, he has to have the software to subtract his speed from the actual speed read to get the apparent speed you are traveling. But even then, there's problems with that. And I'll tell you one of the things that they're getting better at. But you know hills like this? Well, remember I talked to you about the Doppler signature, how it gave an apparent velocity of 69 miles an hour, 68, and there was nothing moving, right? Well, when a cop car comes over a hill and then it's going down, it's going like this, what he's doing is actually changing the point of focus so his beam hits that hill. And he can get all sorts of artifact measurements. Now, you happen to be coming down and going up, then he may see your speed as a much higher speed, but in fact, it may not be. And that's something, if he's a trained officer, he'll realize that it's probably an artifact. But if he just wants to write a ticket, then, it's very hard. You're never gonna be a cop in a court of law unless there's overwhelming evidence, like GPS data or something like that. But that's something to keep in mind. And here's what I mean when I say this, and this is where clutter comes in, because the clutter backscatter causes the most problems with Doppler. That's really where I'm going. So, if you just think about this, if you have a plane moving this way at a certain velocity v, and it's impacting the ground, there's an apparent velocity that ground looks like. The rate of closure would be the actual Doppler, would translate to Doppler velocity, even though nothing's moving. Is everybody following? When the plane does this, now the apparent velocity is huge, all right? And it looks like there's something with a huge Doppler velocity, because the point, you might say the target point the radar's pointing at is got an apparent velocity that's huge. And you have to be aware of this. And also, if he was coming like this and went this way, you would get the same effect, only the velocity would be positive, not negative. Got that? So clutter, this clutter is what I'm calling it. The things, the unwanted reflections is clutter. And this is how we actually figure out how to reasonably calculate it, and then when we do calculate it, how do we get to the signal processing part, how to mitigate it. And here's something. So when we talk about, I just wanted to mention, I've got these written down. Be aware of the divergence factor. I'm not going to actually give you a problem with it. Now with clutter, here's what you need to know. First, we talk about clutter. We don't worry about the Doppler. We want to find a way of giving it an effective radar cross section. That's our real goal on this one. So in the book, the first thing you have to do is figure out how much of the surface is illuminated. And let me just go through this. If you have a certain radar here, and it's got a beam width, and we're going to do beam width here. It's got a beam width. This is the 3 dB beam width. Well, that would actually be phi, but phi, right here. And assume phi 3 dB is equal to theta 3 dB. All right? So it's basically a circular thing. It's a conic going out. Now, when it hits something out here at a range R, then, that's not drawn very well, but what you end up with is something that has an apparent area here, A, which would be pi, all right? Now, the radius of this is interesting, because the radius of this is actually going to be R, right, times the tangent of the beam width over 2, for 1, and it would be actually squared. And here's what I'm doing. In case you don't see it, just so you see it. If you have something and the beam width, this you have to watch, because this is what this proof's based on. If the beam width here is theta, everybody with that? Now, if this is R, right here, and we're assuming beam width in both planes, both vertical and horizontal, or azimuth and elevation is the same, then this height, right here, this would be theta over 2. This height would be R times the tangent of theta over 2, or phi over 2. Y'all agree with that? Opposite over adjacent, opposite here over R, tangent of that angle is this, therefore multiplying R by tangent theta over 2, is that right? Now that is circular, so the actual area that's illuminated would be pi R tangent theta over 2 squared. If the beam width is different in one plane than the another, this is where you write this down. You should have this one. If you talk about now the beam width is different, then what you end up is this. The area here, I'm going to write it down. I think I can kind of hand wave this one. Then the actual area will be pi, and it will be R squared. I'm going to pull the R squared out of that. But then you're going to get the tangent of theta 3 dB in one plane over 2 times the tangent of theta, or phi 3 dB over 2. So it's multiplied by always the beam width by 2, and I mean the tangent of the beam width by 2. Something that happens too, if these angles are very small, like maybe 2 or 3 degrees, tangent of x is about x, so is sine of x about x for very small angles. So now a lot of times what they do, and you'll see this in equations, you'll just see pi r squared, and it'll be the two angles in radians, multiplied by each other, divided by 4. They're all the same thing, there's nothing funny, it's just that's when it's an extremely small angle. And you can check this out, for 2 degrees or less, when it's translated to radians, you don't need to take the tan. That's pretty much the same thing. The tan of the angle is the angle in radians, and that's important. Now that's when the spot size, that's when we're just broadcasting or striking the thing, we're going right at the ground. Follow me with that? That's how big the area is. Once you have the area, you're going to be multiplying it by a backscatter coefficient to get the effective radar cross-section, and that is what you weigh the power density, the input power density with, to figure out how much is coming back at you. Does that make sense to everybody? Just so everybody knows this. Now, we get to the next level of problem with clutter. And I'll tell you one thing, the amount of backscatter from metal, a very good conductor, is very large. The amount of backscatter from grass and forest goes way down. And if this thing was sand, it would be a very little reflection at all. So keep that in mind too. Surface, what makes up the surface has a great deal to do with how much backscatter or clutter signature you get. That's important. Next. Can everybody appreciate this at least? This is chapter 5 too. And it's talking, I'm trying to hit the high points of chapter 5 with clutter. I need to do this before I move into the signal processing because he deals so much with clutter signature. You have to do it. You have to show people what clutter is. Now here's another thing, and that's just area, that's not the clutter, I mean the velocity, Doppler velocity of clutter. It's just the area, and that's planar. All right, now what happens when we have this? When all of a sudden, I've got a radar up here, it's downward looking, here's the center of the beam, but now I've got this kind of effect where I have, this is going to be the actual beam width, but this isn't drawn very well, but I'm trying to show you that this would be the beam width over 2, this is the beam width over 2. Now just look at the area illuminated as if you took a flashlight and looked at a spot. I mean, if you look at take a flashlight and just aim right there, you see a circle, it would be the same kind of effect. You could say pi r squared times the tangent of whatever the effective beam width of the tangent, the beam width of the flashlight divided by 2 squared would be about the area you see, right? But as I take that flashlight and now I aim at an angle, what I get is an ellipse. And it broadens a great deal. As a matter of fact, as I take that beam and I shoot it almost planar to the ground, now the area goes to infinity. Does everybody appreciate that? All right, now, so how do we deal with that? Well, the real truth is this effective broadening of the area right here will be the area itself divided by sine of this angle. All right, and if you take a look at it, just think about this naturally. Right? Here I've got something like this, and I draw a perpendicular to it, and then I do this. Well, this was the original area, right? If I take, and this was the angle right there, this is the angle right there, well, I'll show you that. When you take a look at that, if I take opposite over hypotenuse, it's the sine of that angle, isn't it, class? Do y'all follow me on this? Opposite, the hypotenuse is here, that's what we want. So if I want this, I take this and divide it by the sine. Do y'all see what I'm
So
doing?
the top corner is supposed to be right.
This is the area A. I'm trying to say this is A. What's the
Right.
projection of A here?
Yeah.
All right, it would be A divided by the sine. Now, they don't use sine. They don't have A over sine. What they're going to do is say, in the book, it will be A, then it will be cosecant. All right, because cosecant is the same thing as 1 over sine. I don't like using cosecant, by the way, and I don't like using secant, because most of the time, this day and age, everything we write in computer programs that I've dealt with are always sines, cosines, and tangents. Those are the essential functions you need. You really don't need a secant unless you're trying to do and actually you don't need it at all, but when you do some of these proofs like integration of square root of a squared plus x squared to some 3/2 power, you do a secant squared substitution, but it's really not useful for a lot of things. The essence is sine, cosine, and tan. Okay, does that make sense, everyone? That's being broadened, and now you have to talk about 2 different things that happen when we talk about illumination. Now, and I'll be very clear when I get to the formula formulas and the problems, but I'm just trying to give you an overview. All right, if I'm aiming a radar at an angle like this and shooting at it, right? There's one thing you know, radar is made out of on-off signals, right? The length of time that it's on tells me in space the actual distance I would be illuminating if I froze time. So speed of light times the on-time tau tells me this distance, right? Now think about this rationally. Here, I'm going to put my radar here. I'm going to try to do it like this, right there. But now what I'm going to do is take a snapshot in time and just isolate on one pulse. And I'm going to say, it's basically that. This part of space is actually going to be energized, have electromagnetic energy. This energy is propagating that way. Can you all appreciate that? We froze time. Now let it propagate. What happens a little bit longer down the line? Well, it comes to the point where when it hits here, you see that not the entire area is illuminated, but just a slice on the ground. It's like a part of a shadow going through there, right? And that's what you have to be aware of. That's called pulse limited, the pulse limited area. And please put that down. What I'm trying to talk about is pulse limited area. And this is going to be used for clutter, but pulse limited is something that I'll show you how to calculate in a second, how you figure out where but you have to appreciate what it is, all right? The other is beam limited, and that's the one that we were doing back here. That's pulse limited. Beam limited is this. When I have a beam limited signal, it's basically this. It comes there. This is effectively the area A, and the actual area illuminated is this, from here to here, and that's simply A divided by the sine of this angle. Make sense, everybody? Right. That is most common, but something you have to know. The smaller that angle gets, the greater the chances are it's going to be pulse limited. If it's, and this should make sense, if I'm looking straight down at something, where there's no, I'm normally instant, right? Well, then the amount of area that the pulse, as thin as it gets, illuminates is going to be the only area, right? There's no progressive shadow on the ground. But as I increase that, when the actual angle decreases between the ground and my radius vector r, now I get that slit of just moving down, and that's much less area. Now we need a way to actually talk about first, what are the different areas, and second, where does the transition take place? And that's what I'm about to do. And I'll tell you, when I do this, I think I have a video of this here. And it's really helpful to actually see an animation, to actually see the differences. There's probably a lot of them out there, but if you could probably Google this, and it's just animation of pulse versus beam limited areas, and they'll have them, I'm sure. But so I gave you, this would be for beam limited. It means all area is illuminated. For this case, I gave you that already. The area that the beam would have on the ground would be pi r squared times tangent of the beam width in one plane divided by 2 times the tangent of the beam width in the other plane divided by 2. And then it's going to be divided by the sine 4 times the cosecant of the actual angle that it makes with the ground. With me? You have the drawing from before. That's just the angle that the radius vector makes with the ground.
It's the same as the angle below the horizontal, right?
Yeah, here, let me draw it for you. What I'm talking about is this. If this is the radar beam right here, this is going to be the angle right there, and it's 1 over the side. And this is assuming this is the earth. Okay? And that's being limited, the entire area. Now, when we go to pulse limited, for that one, I'll try to show you, I think. I'm trying to draw it out here. So if it's pulse limited here, I know that basically what I have is this. I have the area, here's my natural area, right there. The projection here would be the projection of that area. That's area, that would be A prime. And now what happens with a pulse, and I'm going to try to take this, if I can, and flip it this way. What it looks like on the ground would be this. You would have this kind of an effect, where this would be the pulse width, all right, the actual width of the pulse in time, the times, I mean, tau times c, but then it would be, it would be the cosine, I'm trying to figure out this, the cosine of that angle. I'll put the one in the, I'll put it in my book, and we can actually work it in a second, but. Let's say this isn't, it's not hard to see, it's hard for me to draw. But I had good artistic skills, it wouldn't be much of a problem. One 69, the bottom has the one I've shown. Then for the one that's pulse limited, he's got it on page 170. And I'm going to put equation 5 and 9 down. For pulse limited, it becomes pi right there times c tau over 2. I'll tell you why it's c tau over 2, because when we hit, it's reflected. Remember that if you take c tau over 2, that's the range resolution. So it's going to have that, and then it's going to have 2r times tangent of the 3 dB angle over 2 times the secant. It's really 1 over cosine. 1 over cosine of the actual angle. And he doesn't use, he uses this. And this angle right here. Now, I'll try to get through this.
Would there also be a tan of phi3 or?
No, the reason is this, when you're pulse limited, it's the beam width of, it's the vertical beam width that you have to worry about. And, I'm sorry, horizontal beam. It's how broad it is in the horizontal plane, because that will limit the width. And the way it looks here, and I'll try to do this, sometimes
Wouldn't it be like an ellipse?
it's really, if you
Or
take a look at it, it's not
oval.
ellipse, it looks like this. On the ground, this is the footprint on the ground is illuminated. You'll see this. And what you have here, right there, this is due to the beam width in the horizontal plane, which is theta. Unfortunately, remember in EMAG, theta is vertical plane beam. Here it's theta. So if you take a look at this distance here, now remember, from here to here is r, right? From here to here is r, so it's 2r, I mean, it's r times the tangent of theta over 2. And it should be there. Yeah, so this is going to be, this distance right here is 2r times the tangent of theta over 2. That should make sense. Now, this is the harder part. Well, what is the width right here? All right, well, that you have to now think about this in a couple of ways. When I have, try to draw this. When I think of a packet of energy, freeze time, and a packet of energy in the shadow cast on the ground. So I'm gonna make it real thin. Like this. Here's the normal. Right? This is what I'm talking about, that way. All right? Well, this width right here is gonna be C tau over 2. The reason they always do that is because when it's hitting, it's reflecting, and it's the range resolution, right? Now, how much of that really is projected on here? And that's where it gets interesting. So, now, let me try to blow that up a little. I'll do it this way. I know I have C tau over 2 here. That's the actual distance, freeze time, that's the amount, the thickness, you might say, of the electromagnetic energy. Correct, class? Now, what's the projection of that? Well, this is where it gets interesting. This is the same thing as this, and that's delta, right? Well, the projection here, the projection of this onto here, if you look at this, if you take a look at this divided by this is effectively C tau over 2. So that would be, this distance right there would be C tau over 2, and then it would be divided by the cosine, 1 over the cosine of this angle. Can you all see that? Does that make sense to everybody? If I want this and I've got this angle, I want this, I've got this distance. Just put it up here and try to do a better job of this. If I want this distance, and I know this distance is A, and this angle is such, well, I know x over A is equal to the cosine of that, right? So if I take a look at this, if I want A, I take x divided by the cosine, right? Does that make sense? Can you all follow this? All right, that's where this comes from. Well, 1 over cosine is secant.
That's what you use.
And I use that, and that's where this thing comes from. And the factor pi is in here. If you want the truth, this comes from this being a cut right here, a portion of that. If you take the whole circle, it would look like that. That's really a cut of it. It's not infinitesimal thin, so they include that pi for that reason. Okay, so it's beam pulse limited, and where's the transition? Where do you go from one to another, which is a very interesting question, because if you do radar signal processing, and you're developing code, and you know you have a stationary radar scanning down and up, right? The place where it goes from beam to pulse is critical for radar signal processing. And that,
It's critical from a, processing in the real world perspective, not just a theory perspective.
well, I'm talking primarily about radars that are used to guide planes in, like at Atlanta on an aircraft carrier. When you're doing radar signal processing, and you've got to know when you go from beam limited to pulse limited, because the backscatter changes a great deal. Now your clutter signature, the way you're actually going to be eliminating the effects of clutter on that are different. Basically, it's the amount of clutter return that actually changes rapidly. And the process, whenever you have pulse limited, you have to spend a lot more pulses before you actually, whenever it's beam limited, you have to spend more pulses, or it takes more time to cover that area, because the clutter signature is much larger. When it's when it's pulse limited, the clutter signature is much less, because the beam is smaller, the footprint. But when you get into the processing, they're gonna identify a whole host of problems, and we're gonna just cherry pick the ones that are most relative, because there's so many problems with radar. But for aircraft, guiding aircrafts in navigational radars and really search radars, it's critical to know where that separation happens. And to be honest with you, there's a couple other things that you have to realize too. Since I'm talking about this in real world stuff, daytime versus nighttime clutter signatures are hugely different. I think you know that when dew settles and stuff like this, it gets a much more reflective surface and moisture content. So the actual 24-hour cycle always is entered into these signal processing algorithms that they use. And they use them, by the way, you can't, I don't know if a radar, weather radar, maybe not, but any kind of navigational radar or radar that's used to land aircraft especially, has to be aware of where that breakout is. Okay? And so where is it? The way they actually do this, I'm going to say this, the way they figure out where it's equal is this, in terms of distance. They take this area and they set it equal to this area, and they solve for when that occurs, because that's the threshold when you go from one to the next. And let me just give you tell you what it is.
So wait, if you said those two equal, what do you solve for? R?
Well,
Okay.
you have a combination of things. If you look, you're solving for an equation that's in terms of beam width, grazing angle,